The standard workflow for generative AI and most customer relationship managers is straightforward. An agent writes a prompt, and a large language model generates an outgoing email. In heavily regulated industries like real estate and mortgage lending, routing outgoing communication through this standard pipeline creates massive legal exposure. This flowchart illustrates the problem with that standard pipeline. Large language models are designed to sound polished, helpful, and persuasive. To achieve that, they will eagerly generate highly converting text that quietly breaks federal laws. In real estate, an AI trying to sound helpful might point out the quality of local schools or the demographic makeup of a neighborhood, triggering a fair housing violation. Or it might suggest that a preferred lender will save the buyer money, violating the anti-steering rules of the Real Estate Settlement Procedures Act, known as RESPA. Software engineers often attempt to mitigate this by adding phrases like ensure compliance to the system prompt, or by fine-tuning the model on legal texts. General instructions fail against the precise mechanics of federal domain law. Telling an LLM to be compliant does not give it the ability to accurately distinguish between a harmless recommendation and illegal financial steering in thousands of edge case scenarios. Reliable compliance in these environments depends on the system's architecture, moving the burden of safety away from simple prompt engineering. Deploying safe AI in regulated sectors requires a rigid, multi-layered architecture. The system must operate completely independently of the user's instructions. This architectural stack represents a constitutional communication system. The iRES engine sits firmly wedged between the CRM database and the client inbox. Acting as an operating system for communication, this engine intercepts every single message before it ever reaches the send button. Functional security depends on treating every user draft as untrusted data, a reversal of the typical AI-user relationship. The system interprets the draft as raw material for a filter, effectively ignoring any command logic the user might have included. Standard chatbots are inherently designed to obey embedded commands and adapt to user requests. A constitutional system rejects that premise entirely. Defensive engineering demands a system that is literally incapable of breaking the law, even if the user explicitly types out a demand to do so. To handle untrusted user drafts safely, the architecture relies on a strict trust model that dictates exactly how the LLM parses incoming text. Users often attempt embedded jailbreaks, intentionally or accidentally hiding commands within their drafts, such as ignore your rules or compliance approved this message. The trust model neutralizes these threats instantly. The engine is hard-coded to strip, never obey, and never acknowledge any embedded commands. This hierarchy chart maps the priority ladder, the rigid framework used to resolve conflicts between the user's drafted text and federal law. At the very top sit the absolute governance rules, labeled R1 through R15. These immutable laws blindly override anything sitting below them on the ladder. Directly beneath governance is the refuse gate, a secondary mechanism triggered by highly sensitive communication categories, like probate or pre-foreclosure. If a user's core draft is a direct solicitation, like an aggressive push to sell an estate, the refuse gate halts the process entirely. The system refuses to clean the draft and blocks the send. However, if the draft contains a minor, passive mention of a sensitive topic, the system simply strips the violating sentence and allows the rest of the compliant message to pass through. By forcing the LLM to evaluate structural, legal compliance before it ever considers the user's stylistic preferences, the priority ladder eliminates the risk of hallucination. Let's trace a single API call as it processes a legally dangerous, violation-padded user draft. This interface shows a raw text block from an agent. It is packed with claims about a preferred lender saving the client money, alongside mentions of a specific property's equity. Step 1 is extract. The system scans the untrusted text, isolating the agent's core intent, tone markers, and any valid whitelisted links, ignoring the surrounding noise. Step 2 is strip. The absolute rules from the priority ladder are silently applied, actively scrubbing out violations. For example, the phrase preferred partner is instantly deleted because it constitutes a direct RESPA steering violation. The phrase your home on Maple Street is also removed. Anchoring the email to a specific address creates an illegal valuation implication. Step 3 is rebuild. The system reconstructs the core intent using the agent's distinct voice, but places it entirely within compliant framing. The Lunder mention is rewritten to explicitly state they are just one resource and that the client maintains total free choice. Step 4 is verify. Before finalizing the output, the LLM executes a first-pass rescan, checking the newly rebuilt text against the core rules. This semantic transformation preserves the agent's personality while stripping away the specific phrases that create legal liability. But why isn't the semantic transformation we witnessed enough to guarantee total compliance on its own? The limitation lies in mechanical exactness. Large language models are probabilistic engines. They fail reliably at rigid, deterministic tasks. When asked to process whitelisted URLs, LLMs frequently alter the text, shortening the links or hallucinating fake tracking parameters that break the destination. LLMs also have an ingrained behavioral habit of appending conversational sign-offs, like "have a great day." In real estate, this violates CAN-SPAM formatting rules regarding appended elements. This logic diagram outlines the final required layer, the validator. It catches the mechanical errors the semantic engine misses. The validator relies on roughly 100 lines of deterministic code. It acts as an unyielding filter. Even if the LLM allows an unapproved domain class to pass, like a direct rate quote page, the validator definitively strips it before the email can send. True compliance requires stacking a semantic LLM pass for tone, alongside a strict deterministic pipeline for absolute mechanical rule enforcement. This architecture highlights the difference between additive and subtractive content generation. This visual scale shows a subtractive process at work. When a heavily stripped, violation-padded draft hits the governance filter, it shrinks into a thin, generic skeleton of an email. Contrast that with an additive process. When an agent drafts a message based on relationship-building values up front, the content passes through governance largely untouched, preserving a rich and authentic message. A governance layer is purely a preservation tool. It evaluates and filters, but it cannot manufacture good intent if none was provided by the user. A governed communication system is ultimately only as effective as the foundational human values fed into it. The 5-layer architecture of this system offers immense modular potential. The system separates the immutable constitution, which holds universal communication values like autonomy and transparency, from the domain-specific policy packs. This architectural stack demonstrates how the system scales to new, highly regulated industries. The core engine remains stable, while the specific regulations are updated simply by hot-swapping the policy pack. Ultimately, engineering for autonomous agents demands a deterministic, priority-driven runtime that confines the AI to a professional constitution.